Hello, class. Today we're going to continue Chapter 8 in Trigonometry. This is Math 154 at College of the Sequoias. If you're at a different school, it's likely a different number, but the course material isn't really any different. This section is on vectors, and more specifically, the dot product. Okay, so it might be different in your book if you're attending a different school, but the material hasn't changed. The dot product has another name. It's also called the inner product. These two things are interchangeable. Okay. So what we like to do is we like to work with vectors that originate at the origin. And terminate at a point AB. At the coordinate AB. So we've got our x-axis, we've got our y-axis. This is our origin, 0, 0, the origin. And our vector comes out to a point right there and stops right there. This point is A along that axis. This is B over here. So this is the point A comma B. We can see this makes a right triangle. Let's call this vector V. And it makes an angle theta with the x-axis. So vectors that are written this way, vectors that originate at the origin, are called position vectors. Position vectors. Okay. And we write them as such. We will say vector V equals, and then we use those kinds of brackets, and we'll say AB. Those brackets indicate a position vector. That terminates at AB. Okay. Theta is called the direction angle. I believe we've mentioned that before. And this is the degrees or radians away from the x-axis. So it's sweeping out that much of an angle. We can see here, using the Pythagorean formula, that the magnitude of V has to equal, well, remember, we have C squared equals A squared plus B squared. So C equals square root of A squared plus B squared. And this is normally C. So V, the magnitude of V is a squared plus B squared, the square root. And this is, of course, is in 2 dimensions. Notice this also satisfies that the tangent of theta equals B over A. Okay. So let's take a look at some examples. Again, please pause anytime you need to finish taking notes, and please pause to try to work out some of these examples once we've walked through them. Okay. So our first example will be find the magnitude and direction angle of V equals 4 comma -3. So what does that tell us? That tells us we have a vector that starts at the origin and ends at the point 4, -3. This is theta. Which is going to make this angle right here, that'll be theta hat, our reference angle. And this is in quadrant 4. And so let's look at what that triangle is. We got this triangle like this. Let's blow that triangle up a little bit. This length right here is the magnitude of V. So I've got the magnitude of V. This length here was my x coordinate is 4. The y coordinate was -3. So we've got the magnitude of V is the square root of 4 squared plus -3 squared, which is the square root of 16 plus 9. And that's 16 plus 9 is 25. The square root of 25 is 5. It's actually plus or minus 5, but vectors always have a positive magnitude. Only the direction changes. So that's our magnitude. That was the first question. They want to know what theta is. So theta hat, we have tangent of theta hat. Remember our reference angle is B over A, our y coordinate over our x coordinate, -3 over 4, which is -0.75. Got my calculator. What does it tell us about theta hat? Theta hat is tangent inverse of -0.75. -36.9 degrees, maybe. That's theta hat. So what's theta? Theta plus theta hat have to add up to 360. So if we treat that as a positive angle, We get theta equals 360 degrees minus 36.9 degrees. Theta hat is actually going that way, so theta hat's kind of positive. This is just telling us it's down below the x-axis. And we get theta equals 323.1 degrees. And we had a magnitude of 5. Why don't you guys give it a try? Let's come up with a problem for you. What did I just do there? 4, -3. Let's do example. V equal, not that. V equals -5, 4. Find the magnitude and theta. Pause the video. Please try to work that out real quick. I'll assume you paused it. Let's take a look at a picture here. Here's our x-axis and our y-axis. -5 is back this way. 4 is up here. Our vector, position vector, terminates right there. So this is V. That's theta. So this angle right here will be theta hat. We have the magnitude of V is the square root of a squared plus b squared. It's the square root of 25 plus 16 is the square root of 41. Okay. Tangent theta is negative b, or b over a, which is 4 over -5, which is negative 0.8. So what does that give us for theta? $38.659 degrees, 38.67 degrees. 38.6 degrees, or 38.7 degrees, sorry. And that's really negative, and that's saying how much is going back. So the absolute value of that, that's 38.7 degrees. It looks like theta plus theta hat have to add up to 180 degrees. So theta equals 180 minus theta hat, which is 38.7. Is 141.3 degrees. Okay. Now, we can go the other direction. Let's take a look at what else we can do. if we have the magnitude and angle, we can find V. How? Well, let's draw a picture. Let's see if we can reason it out. It's making an angle theta. We know the magnitude of this is V. This side is A, this side is B. So if we look at cosine of theta, cosine of theta is adjacent over hypotenuse. And it tells us A equals the magnitude of V times cosine of theta. Sine theta equals B over magnitude of V, which tells us that B equals the magnitude of V sine theta. This actually gives us another way of expressing V. V is also expressed as the magnitude of V cosine theta, comma, the magnitude of V sine theta. That's if you know the magnitude and direction or angle and not the endpoints. The other way is using the A comma B. Let's take a look at some examples. We'll do one together, then I'll have you try one. So our first example, we don't need to use B every time. Let's change it up. Let's go with W. The magnitude of W equals 16.0. And let's say theta equals 72.3 degrees. What quadrant is this in? It's between 0 and 90. This is quadrant 1. So our picture it's kind of steep. 72 degrees is kind of steep. And this has got a length of 16.0. We're looking for A and we're looking for B. It looks like B is going to be bigger than A. So I can write W is the magnitude of W times cosine theta, comma, magnitude of W sine theta. We get 16.0 times cosine of 72.3 degrees. 16.0 sine of 72.3 degrees. And to 3 significant digits, what do we get? 16 times cosine of 72.3, 4.86. 16 times sine of 72.3, 15.2. Yeah, it's a lot taller than it is. The y value is a lot bigger than the x. Let me give one for you guys to try. We're going to say the magnitude of U, change the letter again, is 7. Say 7.0. Another way of writing theta is sometimes they use the vector as a subscript to tell you what theta that vector is, or what vector theta is applying to. This is 60 degrees. Go ahead and give that a try. Okay, I'll assume you work through it. This one is also in quadrant 1. Let's see, 30, 60, it's about like that one. 7 long, we're looking for A and B. There's my theta. U equals the magnitude of U cosine of theta, magnitude of U sine theta. Cosine of 60. Cosine of 60 is what value? I hope you have this memorized. It's 1/2. So 7 times 1/2. And this is 7 times √3/2. So U is 3.5, 3.5 square root of 3. And we can figure out what that is. (3.5, 6.1) to 2 decimal places or 2 figures. Ready for another one? Let's do V again. V, the magnitude is 3. And theta for V is 270 degrees. Okay, if you drew a picture, 270 degrees is where? Straight down, right? We should have an x value of 0 when we're done. Let's give it a try. Let's check it out. Magnitude of V cosine of theta, magnitude of V sine of theta. 3 cosine 270, 3 sine of 270 degrees. And this is, of course, 0 and -1. V equals 0, -3. So that's another way of looking at vectors. We haven't even looked at the dot product yet because dot product was a form of multiplication. Let's look at doing addition and subtraction in this version. So let's look at mathematical operations on vectors, or arithmetic operations on vectors. So we're going to do, this is vector U, and this is vector A comma B. This is vector B. And we can also look at that as C comma D. Which is telling us what? This value right here is C. This value right here is D. This value right here is B. This value right here is A. And now let's look at adding them. Remember, when we add vectors, we do tip to tail. We can make a parallelogram. So this will be U plus V. How far over have we gone on this part? What is this value right here? What we've done is we've taken, if we move this vector over, what we're really doing is making a distance A right here, which means that coordinate is C plus A, or A plus C. And if we move this portion up, what we've really done is moved it up a length D. D. So that value is B plus D, or D plus B, however you want to look at it. So what just happened there? Those are our coordinates right there. It looks like A comma B vector plus C comma D vector equals A plus C comma B plus D. In this form, vector addition, we add the individual components. This is pretty easy. If you know A, B, C, and D, this is a basic operation. Guess what that does to subtraction? If we have A comma B minus C comma D, this is the same thing as A comma B and adding the opposite vector. And we get A minus C, B minus D. So what we're doing is subtracting individual components. This stuff is almost all of Calculus 3 depends on you being able to do stuff with these vectors. Calculus 3 tends to be three-dimensional calculus. Right now, we've only been working in 2 dimensions, but when you get to Calculus 3, this gets kicked up a notch. And then we can look at multiplication. We have our scalar multiplication. Some value k times the vector AB equals k times A, k times B. Same thing with if U equals AB, -1 times AB is -A, -B and that's negative u, just like multiplying that by -1. That's scalar multiplication. Let's do a few things with those things before we get to the dot product. So let's look at some examples. Okay. First example, u equals 3, 4. B equals -2, -3. Goal A, find u plus v. So this is 3, 4 plus -2, -3. We add the individual components, 3 plus -2, 4 plus -3. And we get the vector 1, 1. That's u plus v. We can try something different. Let's find -3v. So we'll take b and multiply it by -3. And that's +6, +9. And so why don't you guys make it a little bit more challenging? Let you try guys one, combine these. Let's do like 2u minus v. Try working that out. I'll assume you paused it. You got 2 times 3, 4 minus -2, -3. If I move the 2 inside, 2 times 3 is 6. 2 times 4 is 8. And I can move the negative in sign if I make this addition. 2, 3. We just add the components. So 2u minus v is 8, 11. You guys ready to try one with a bunch of options on your own? Okay. Let's go with, we'll say v equals, what did I use in the last one? I want to have them different. B equals 5, 1. W equals 3, -2. Your goal is to find u plus or v plus w. And then find 3v minus 2w. Go ahead and pause it. Okay. What do we have here? 5 plus 3, 1 plus negative 2. And that turns into 8 comma negative 1. This one I've got 3 times 5 comma 1 minus 2 times 3 comma negative 2. I'll distribute these in. 3 times 5 is 15. 3 times 1 is 3. I'll distribute the negative 2 in, making this positive. Negative 2 times 3 is negative 6. Negative 2 times negative 2 is 4. We add the individual components. And we get 9 comma 7. Okay, there's another way to discuss these vectors. I want you to learn about them. This is another very, very handy way. We have something that are called unit vectors. Unit vectors have a magnitude of 1. They can point in any direction from the origin. The two most common unit vectors are along the x and the y axis. So let's say this is x, this is y. This length here has a magnitude of 1. This length here has a magnitude of 1. The only way to get that, remember, we have to have a squared plus b squared is the square root, and that's got to equal 1. Along these, here, b is 0. So for the x1, x-axis 1, b is 0. So I've got the square root of a squared plus 0 squared equals 1. Tells us a equals 1. This vector is 1 comma 0. And they write an I with a hat on it. That's my I. I put a little tail on the I so it looks like an I. This is called I hat. Likewise, on this one, here a is 0. So 0 squared plus b squared equals 1 gives us b equals 1. And the vector is 0 comma 1. And that goes by j hat. How is this helpful? In the last example, W equaled 3 negative 2. I can write that as 3 times 1 comma 0 minus 2 times 0 comma 1. So W hat is 3I hat minus 2j hat. This is another way of writing vectors. and works well with dot and cross product. Now, cross products you're not going to learn in this course. It's a three-dimensional concept. You can't have a cross product in 2 dimensions. It's definitely 3 dimensions, but dot product can be done in 2 dimensions. So let's take a look at the dot product. The dot product or inner product. If I have a vector u and it's AB, and I have B and it's CD, or u equals AI hat plus BJ hat, B equals CI hat plus DJ hat. U, the vector U dotted with vector V, this is what it looks like, is equal to A times C plus B times D. This is read as U dot V. Note, neither of these are vectors. This is a scalar outcome, or just a number. And the idea of it is it's the sum of the products of the x components and y components. Before we go on, before I go through the general properties, I want to show you how this works here. What we're doing is we're taking AI and multiplying it by CI, J dotted with DJ. Now, I haven't told you the property yet, but it works like this. We can take the AC out. We've got A times C, and we've got I dot I plus B times D, J dot J. What is I dot I? One zero dotted with 1 0 equals 1 times 1 plus 0 times 0, which is 1. J hat dot J hat, 0 1 dotted with 0 1. We multiply the first 2 numbers, 0 times 0. We add it to the multiplication of the second 2 numbers, 1 times 1, and we also get 1. So this gets us A times C plus B times D. It results in the same thing as doing it with the position vector form. Okay. You will find it's very interesting. What is I dotted with J? This leads to a very valuable concept of the dot product. 1, 0 dotted with 0, 1. We multiply the first two components and we add multiplying the second two components. 0 plus 0 is 0. What does that mean? Let's look at I hat and j hat. I hat's there, j hat's there, and we just showed I dotted with j equals 0. What relationship do I and j have? They're perpendicular. I and j are perpendicular. In vectors, we call perpendicularity being orthogonal. These are our orthogonal vectors. The dot product of orthogonal vectors is 0. And I'll show you that again in another second, in another way. Okay. So the properties of the dot product. Let's take a look at those. We have all of our general rules that we're used to in math. They transfer over to vector properties. If I dot u and v, I can change the order and do v dot u. This is the commutative property. Remember, a times b equals b times a. And a plus b equals b plus a. We showed the a plus b equals b plus a in 8.3. Here it applies. Another property we had was the associative property. If I have u dotted with v plus w, this is the same thing as u dotted with v plus u dotted with w. And we can change that order, of course. We've got u plus v dotted with w is u dotted with w plus v dotted with w. So these are the associative property. And all you're doing is distributing the dot product. If we throw a scalar multiple in, if I have some constant k and I multiply it by u dotted with v, I can put it with the first one. I can make it ku dotted with v. Or I can make it u dotted with kv. Don't do k with u dot v equals ku dot kv. What you've done is you've done a k squared there, not k. Don't do that. This is bad juju right there. No. What happens when we multiply anything by 0? This transfers over just fine. It's 0. Oops, not a vector. Dot product does not result in a vector. And we've got u dot u. Let's take a look at that. This is ab dot ab, which is a times a, or a squared, plus b times b, or b squared. This looks a lot like, what if I wrote this as the square root of a squared plus b squared, and I squared it? What is this right here? That's the magnitude of u. So another way they often write u dot u is it equals the magnitude of u squared, which is a squared plus b squared. This is a handy notation to get used to. It pops up a lot. Okay. Ready for some more? So what was our law of cosines? We had c squared equals a squared plus b squared minus 2ab cosine of angle C. Okay, let's see how this applies to vectors in this form. Say I've got vector u, vector v. We'll call this v1, v2. We'll call this one u1, u2. Subtracting the vectors, adding the vectors is this one. That's u plus v. That is u minus v. And so what do we have here? This is the magnitude of u. And this is the magnitude of v. So let's look at that without that extra little bit I put in there. We've got u and v. This is our angle theta. And this gives us our side C of a triangle. And to be consistent, let's call this W, vector W, which is u minus v. So C squared equal, we're following this pattern. This is like A, this is like B. Vector W squared equals the magnitude of u squared plus the magnitude of v squared, that's my a squared plus b squared, minus 2 times the magnitude of u times the magnitude of v times cosine of theta. And where do they come up with this next thing? I'm going to show you. What happens when theta is 90 degrees? Well, magnitude, when that happens, c squared equals a squared plus b squared, which means magnitude of w squared equals magnitude of u squared plus magnitude of v squared. And let's plug that in up here. I'm going to replace the u squared plus v squared. I'm going to replace this part. And then I'm going to subtract the magnitude of w squared from both sides. This is just a value. And I get 0 equals -2 magnitude of u, magnitude of v, cosine of theta. If I divide by -2, I get 0 equals magnitude of u, magnitude of v, cosine of theta. Does that make sense so far? These are perpendicular vectors or orthogonal vectors. I told you when orthogonal vectors have a dot product of 0. We worked it out with I and j. Well, the 0 is right there. So the end result is another way of doing u dot v is the magnitude of u times the magnitude of v times cosine of the angle between them. So I'm going to write that out in words because this is important. U dot v equals magnitude of u, magnitude of v, cosine of theta. This is box it. Know this. Dot product is the product of the magnitudes times the cosine of the angle between them. Cosine and angle between them, this is often called the inner angle, which might be maybe why they call it inner product. Now, true, up here to do this, I had theta equaled 90 degrees for this problem. but this overall principle holds. Notice what happens if I isolate cosine theta. I'll divide by the magnitude of u and v. And I get cosine theta equals u dot v over the magnitude of u times the magnitude of v. And ideally, theta is between 0 and 180, because otherwise we're just going the other way. If the angle is bigger than that, we're just making a triangle going the other direction. So what happens when theta is less than 90? This leads to an acute angle. So u v theta. And you'll end up finding that u dot v is greater than 0. It's positive. And we had when 90, I don't want the less than or equal to part. Just the less than. I'm going to rewrite those symbols. 0 less than 90. (90° less than theta, less than 180. We have an obtuse angle. Here, u dot v is less than 0. And right smack dab between them, when theta equals 90°, as we showed earlier, u dot v equals 0. Notice that holds true in this formula. U dot v equals magnitude of u, magnitude of v, cosine of 90°. But cosine of 90° is 0. That's another way of showing u dot v equals 0. And let's look at doing an example. We've got u equals 2, 5. V equals 1, 3. Find u dot v. And theta, the angle between them. Well, the easiest way to do this is not going back to that cosine theta formula. U dot v is 2, 5 dotted with 1, 3. We just multiply the x values and add that to the product of the y values. And we get 2 plus 15 equals 17. This is greater than 0, so theta should be less than 90 degrees because u dot v is positive. How are we going to find theta? We're going to use cosine of theta equals u dot v over the magnitude of u times the magnitude of v. We already have u dot v. This is 17. Which means we just need to find the magnitude of u and the magnitude of v. It's the Pythagorean formula. We've got 2 squared plus 5 squared for v, or u. Square root of 4 plus 25 is square root of 29. Magnitude v is 1 squared plus 3 squared. 1 plus 9 is 10. Which means the magnitude of u times the magnitude of v is the square root of 29 times the square root of 10, which is the square root of 290. So cosine theta equals 17 over the square root of 290. Theta equals cosine inverse of 17 over the square root of 290. And let's figure out what that is. That's 17 divided by the square root of 290. And then I'll do shift cosine to get cosine inverse. I'll say do the answer. And I get 3.37 degrees. Does this sound right? Let's take a look. Let's draw it. That's vector u. That's vector v. Yeah, the angle between them is small, right? 3.37 degrees looks about right. Looks about right. Okay. Let me give you guys one to try. So find u, the magnitude of u, the magnitude of v, u dot v, and cosine of theta. Given u equals 3 comma negative 4 and v equals 4 comma negative 3, 4 comma 3. I hear someone outside. Interesting. All right. I'll pause and let you work on it. Okay, so what's the magnitude of u? Square root of 4 squared and 3 squared. Square root of 16 and 9 is 25. That also equals 5. U dot V that equals 3 times 4 plus negative 4 times 3. This is 12 plus negative 12, which is 0. So U dot V equals 0. Cosine of theta is U dot V over magnitude of U, magnitude of V, 0 over 5 times 5. 0 over 25 is just 0. Which tells us theta equals 90 degrees. And we knew that from that. That also told us theta equals 90 degrees. Let's draw those vectors. Is it 90 degrees? I'm going to try to make sure these are all spaced evenly apart. 3, negative 4 is down here. 4, 3 is right there. That's angle theta. And if I drew the picture better, this looks like 90 degrees, looks reasonable. Especially since I was freehanding it. That wraps up 8.4. All right. I hope you guys we're almost at the end of the semester. Keep hanging in there. I'll have the rest of these videos up for chapter 8 this weekend. Peace.